Megan, if Earth had taken just one wrong turn in its cosmic journey, a slight nudge closer to the sun, a shift in atmospheric chemistry, or a missing, invisible shield end today, instead of blue oceans and green forests, we'd be a scorched wasteland, not unlike our sister planet Venus. But something saved us. And scientists now believe it's not just chance, it's a newly discovered planetary force field, a cosmic guardian that protected Earth from becoming another Venus. This revelation didn't just rewrite what we thought we knew about magnetic fields at S, turning our understanding of planetary survival inside out. It's subtle, invisible, and for a long time, we didn't even know it was there. But without it, Earth might have lost its air, its water, and us. Venus, in so many ways, is eerily similar to Earth. Roughly the same size, mass, and composition, both planets likely started with similar amounts of water. Yet one is a lush cradle of life, and the other is a searing inferno with surface temperatures hot enough to melt lead. How did two sibling planets turn out so differently? That question has haunted scientists for decades. And now, thanks to a mix of high-orbit satellite data, simulations, and deep space observation, researchers may have found the answer on. It's both shocking and a bit humbling. The Earth didn't just luck out. It had help, a kind of planetary shield more intricate than we imagined, and it kicked into high gear right when we needed it most. This force field isn't like the sci-fi domes you see in space movies. It's not visible, you can't touch it, and yet it shapes everything. For a long time, we thought Earth's magnetic field, generated by our spinning iron core, was the main player in shielding us from the sun's rage. And to a large extent, that's true. The magnetosphere protects us from solar wind, those charged particles that would otherwise strip away our atmosphere. But recently, scientists discovered that this magnetic cocoon has a surprising partner, something that changes how solar particles interact with the Earth's upper atmosphere, and which might have been the very thing Venus lacked when it needed it most. It's called the ionospheric barrier. And unlike Earth's well-known magnetic field, this layer exists high in the atmosphere and behaves like a reactive, dynamic shield, more fluid than rigid, more intelligent than static. It forms where high-energy particles from the sun interact with Earth's ionized upper atmosphere, creating an electrically charged layer that responds almost like a living membrane. And it's this layer that might have saved Earth when the young sun, in its volatile youth, was bombarding the inner planets with a torrent of radiation strong enough to rip the air off any planet without protection. The revelation came as part of a comparative mission involving data from NASA's MAVEN spacecraft orbiting Mars, the ESA's Venus Express probe, and Earth's own Themis and cluster missions. Researchers noticed something curious. Even though Earth and Venus both had early atmospheres, only Earth retained its water-rich climate. Venus lost its oceans in what scientists call a runaway greenhouse effect, an irreversible loop where heat trapped by the thickening atmosphere caused more evaporation, which in turn thickened the atmosphere even more, until the planet boiled dry. But what triggered that cycle? And why didn't Earth fall into the same trap? Turns out, the presence of this dynamic ionospheric barrier might be the key difference. When the sun's radiation slammed into the Earth, this upper layer absorbed and dispersed the energy, preventing the solar wind from directly hitting and stripping away lighter gases like hydrogen and oxygen, the building blocks of water. Venus, on the other hand, lacked this response system. Even though it had a magnetic-induced field from solar interactions, it wasn't strong or responsive enough to stop the loss. The sun basically peeled away Venus' protective layers like an onion. Earth's layered response, on the other hand, acted like armor that regenerated in real time. Even more astonishing, this force field isn't constant, it fluctuates based on solar activity, expanding during solar flares and retracting during quiet periods. In essence, it's alive, always adapting to the sun's mood swings. Some scientists have even begun to refer to it as the planetary immune system. And just like the immune systems in our bodies, it doesn't just block intrusions, it learns, responds, and evolves. The idea that a planet can react to solar danger in real time, thanks to the electromagnetic choreography of charged particles in its upper atmosphere, is a game. And here's where the story gets even more incredible. During one of the sun's early tantrums, some 4 billion years ago, it unleashed what's called a burst of radiation thousands of times more powerful than anything seen in modern history. Based on simulations and geological records, this event should have sterilized Earth. Mars, which lacked any protective magnetic field, lost most of its atmosphere shortly after. Venus began its long slide into atmospheric chaos. But Earth, the ionospheric barrier, thickened, reacted, and bounced the worst of the energy back into space. That one act of defense may have preserved the conditions that allowed life to flourish. It's not that Earth was simply lucky, it's that it had just the right balance of ingredients to form this self-regulating barrier. Thanks in part to our unique rotation, the presence of a moon to stabilize our tilt, and the dynamic dance between our core and our atmosphere. All of these contributed to the emergence of this force field. It's like a recipe. Remove one ingredient, and the whole thing collapses. The fact that Venus didn't have the same result underscores just how precarious planetary evolution really is. The research community was initially skeptical. After all, how could something so vital have gone unnoticed for so long? But when data from multiple missions lined up, and atmospheric loss rates on Venus were compared with the relative stability of Earth, the evidence became overwhelming. Earth's barrier, ISNT, just a scientific curiosity, it's a defining feature of why we're even here, and understanding it could shape how we search for life elsewhere in the universe. If an exoplanet doesn't have signs of a responsive ionosphere, its chances of long-term habitability could be far lower than we thought. Regardless of how Earth-like it looks on the surface, this discovery also raises an unsettling question. What happens if this barrier fails? Could human actions like altering the atmosphere's composition, increasing radiation from artificial sources, or even large-scale electromagnetic interference disrupt its delicate function? While the short answer is that the barrier is remarkably robust, the long-term implications of poking at this invisible guardian are still unknown. It's yet another reminder that Earth is not invincible. We live under the protection of forces we barely understand, and those forces are not guaranteed to last forever. But there's also hope in this, because by learning how this ionospheric barrier formed and works, we might one day replicate it. Imagine deploying artificial ionospheric shields around future colonies on Mars, or building defensive layers around spacecraft using what we've learned from Earth's own atmospheric defenses. The idea of electromagnetic bioshields no longer sounds like fantasy. It sounds like future engineering, and it started with a discovery that, until recently, was hiding right above our heads. Back in the early days of planetary science, we assumed that atmospheres were mostly static blankets of gas that planets either kept or lost based on mass and distance from the sun. But we now know they are alive, shaped by forces more complex than gravity or temperature alone. Earth's upper atmosphere doesn't just float, it fights. It resists, it protects, and it does it so silently and invisibly that most of us never think about it. But if you've ever walked through a forest, stood in the rain, or looked up at the stars without suffocating or burning, you've benefited from it. The research continues, with satellites constantly feeding data back from Earth and Venus, and AI models simulating planetary behavior on timescales we could never observe directly. And every bit of that data seems to support the same conclusion. Earth's survival, ISNT, just due to location AS, due to innovation, not ours, but nature's. A self-made force field, a barrier born of electromagnetism, chemistry, and timing, a planetary miracle hiding in the math. And as we face a future where solar storms may intensify, where space travel becomes common, and where protecting human life in hostile environments becomes urgent, this discovery couldn't have come at a better time. Earth's ionospheric barrier, ISNT, just the reason we realive it, might be the blueprint for how we stay that way, even beyond our home planet. Stay tuned for part 2, where we'll dive deeper into how this discovery might change our approach to the ongoing mysteries of Venus' lost water, and whether planets around other stars could ever recreate Earth's miraculous defense system. But one thing, already clear. The sky, ISNT, empty it, fighting for us. What if we told you that Earth's greatest protector is something you can't see, can't touch, and didn't even know existed until recently? Chapter 1 revealed the staggering truth that an invisible, reactive force field in Earth's upper atmosphere may have spared us from a fate like Venus. But that revelation opens up an even bigger question. What can we do with this knowledge? Because if this barrier saved us once, could it be used again? Could it help us terraform planets, protect spacefarers, and perhaps even turn uninhabitable worlds into thriving ones? The deeper scientists dig into this mystery, the more it feels like Earth's ionospheric shield, ISNT, just a relic of survival at S. A blueprint for the future. Let's rewind for a second. When scientists first began studying planetary atmospheres in the 20th century, the focus was on the basics: composition, pressure, and escape velocity. The prevailing wisdom was simple. A planet keeps an atmosphere if it's big enough and far enough from its star. But now we know that equation is incomplete. Earth and Venus are practically twins in size, but Earth has oceans and breathable air, while Venus has a 90-atmosphere thick cloak of carbon dioxide and sulfuric acid clouds that rain acid and trap heat like a prison. The missing variable, it turns out, wasn't just magnetism, it was this dynamic ionospheric response system. And once scientists figured that out, everything changed. Think about what this means for planets like Mars. Mars is cold, dry, and airless today. But evidence shows it once had rivers, lakes, and possibly oceans. It's also much smaller than Earth. And crucially, it lacks a global magnetic field. Over billions of years, the solar wind stripped away its atmosphere, turning a potentially habitable world into a barren wasteland. But what if Mars had possessed an ionospheric barrier like Earth's? Could it have survived? Could life have flourished there too? Some scientists believe the answer is yes, and now they're reworking on a radical idea, creating an artificial magnetic shield at Mars L1 Lagrange point, a location in space where a satellite could remain fixed between the planet and the sun. The goal? Recreate what Earth has naturally. This isn't science fiction. NASA and ESA scientists have already modeled how a magnetic dipole placed at L1 could redirect solar particles away from Mars, allowing the atmosphere to slowly rebuild itself over centuries. Combine that with greenhouse gas generators, and Mars might be able to warm enough to support liquid water again. In essence, we'd be replicating the Earth's electromagnetic armor, piece by piece, and the discovery of Earth's ionospheric barrier gives that dream new momentum because now we know what to aim for. We're not just trying to protect planets from radiation. We're trying to recreate the complex, layered defense mechanism that allowed life to persist on Earth despite the wrath of the sun. But Earth's shield isn't invulnerable. In fact, it's constantly under assault. Solar storms, coronal mass, ejections, and flares pound the upper atmosphere with billions of tons of charged particles. In 1859, the infamous Carrington event caused telegraph systems across the world to spark and fail. If a similar event struck today, our satellites, power grids, and communication networks could be wiped out in minutes. The only reason Earth wasn't devastated then or now is because of the layered response of the magnetosphere and ionosphere working together. During major solar flares, the ionospheric barrier swells, shifting from a passive shield to an active absorber. It essentially catches the solar energy and converts it into harmless auroras rather than letting it fry everything below. That process isn't random. It's orchestrated by changes in ion density, electromagnetic wave propagation, and field-aligned currents that flow along Earth's magnetic poles. These currents trigger shifts in the upper atmosphere, thickening it at just the right moment to prevent disaster. The more we learn, the more this system looks less like a simple field and more like a reactive neural network sensing threats, adapting and responding in real time. And that level of sophistication is what Venus lacked. It had some induced magnetic properties, but they were too slow, too weak, and too disorganized to mount a defense. When the solar wind surged, Venus couldn't adapt. Earth did, and we're still here. But now, researchers are asking, could other planets develop such barriers under the right conditions? And even more exciting, could we build them ourselves? The idea of artificial ionospheric systems isn't entirely new. In fact, experiments like HAARP have been studying how to stimulate the ionosphere using radio waves for decades. These tests were initially designed for communication and radar research, but they revealed something fascinating. With the right frequency, we can temporarily alter the density of charged particles in the upper atmosphere. It's rudimentary compared to Earth's natural system, but it proves a point tower atmosphere is programmable. And if it's programmable, it's replicable. Imagine, then, future space colonies on Mars or the Moon, wrapped in artificial fields generated by massive orbital coils or satellite arrays, designed to mimic Earth's electromagnetic dynamics. These systems wouldn't just deflect solar wind, they'd respond to it, expanding during flares, contracting during lulls, and protecting everything inside. We're standing on the brink of a new frontier, not just in colonization, but in planetary engineering. Earth didn't just survive, it engineered a survivable envelope. Now we know what that envelope looks like. The next step is creating one wherever we go, and this changes how we search for life too. Until now, astronomers have focused on the so-called habitable zone, the sweet spot around a star, where a planet's temperature allows liquid water to exist. But that definition is incomplete. We now know that habitability also depends on atmospheric protection. A planet might orbit in the perfect zone and still be sterile if it lacks the right atmospheric defenses. That's why the discovery of Earth's ionospheric shield is so monumental. It tells us we need to look for electromagnetic signatures, not just chemical ones. It's not just about what's in the atmosphere, it's about how the atmosphere reacts to solar radiation. New missions like the James Webb Space Telescope and future exoplanet explorers are now being tuned to detect these subtle electromagnetic clues. Researchers are developing algorithms to spot signs of ionospheric behavior in distant worlds, sudden shifts in radio emissions, particle absorption signatures, and ultraviolet patterns that suggest reactive shielding. If we find a planet with those markers, it might be the closest thing to Earth we've ever seen. But as we look outward, we're also realizing just how delicate Earth's own system is. Climate change, rising greenhouse gases, and thinning layers of the upper atmosphere could all interfere with the performance of the ionospheric barrier. Some scientists warn that if we alter the atmospheric chemistry too much, we could disrupt the very dynamics that protect us. It's like tampering with the nervous system of a living organism. You don't always know what the side effects will be. That's why this discovery comes with a responsibility. We now know what protects us. The question is, will we protect it? Even the moon, long thought to be just a dead rock, may have played a role in shaping this outcome. Our moon stabilizes Earth's tilt, influencing the seasons and ocean tides. But some researchers believe it also helped Earth maintain a stable rotation rate, which is essential for the dynamo effect that generates our magnetic field. Without that, our magnetosphere might never have formed. And without the magnetosphere, the ionospheric barrier would never have functioned. It's a cascading series of lucky events and cosmic alignments, each dependent on the other, all leading to this one outcome. Life, as we know it, is fragile. But thanks to this invisible force field, it's also surprisingly resilient. From bacteria deep in the ocean trenches to astronauts in orbit, life thrives within the bubble this system creates. When solar storms rage, when cosmic rays lash out, we are insulated by an atmospheric genius we didn't even know existed until now. The more we learn, the more grateful we should be. Because Earth didn't just give us a home, it gave us a shield, a guardian, and perhaps even a future beyond this world. So next time you look up at the sky, remember, the quiet stars hide a violent storm. The calm blue above your head is a battlefield. And somewhere up there, in the whisper-thin layers of air and ion, Earth is fighting for you every second of every day. Like and subscribe to Beyond Stars for more awe-inspiring discoveries and cosmic secrets. Because the more we understand our universe, the better we can protect our place in it.